would like to use your liquid chromatograph. And being an old hell yes guy, I let him do it and start getting interested in this project on trying to determine if there's a repellent. There was clearly a repellent. When you cut down an aspen tree, it sends up shoots. Beavers won't touch them. There's some evolutionary process. I'm not going to take all of Drew's thunder, but anyway, he started looking at that. He isolated, and indeed that there was a compound, big peak in HPLC that wasn't in the mature form that he isolated and painted it on branches, and it was fine. And so we had an isolate of that, and we took some NMR, got some NMR of Davis, and another graduate student was working that, never got it. He got close, but he didn't get it. And then I wanted to have this finished. I have more years behind me at UNR than ahead of me. And Drew was interested in a project. I mentioned this, and he was interested in synthetic organic chemistry, and now we talked to Chris Jeffries, and he's a oh hell yes, we can do that kind of guy. And I think he's gotten in trouble probably as much as I have with that attitude. But it was very good. And Chris was very instrumental in knowing the literature a lot better than I did in that area, and found some work that had been done. Anyway, the bottom line is that wanted to synthesize material to see if it was actually the right structure, and that's what Drew has been doing, and he's done an excellent job. I'm the chairman of Drew's committee. Chris has done all the advising effectively, so I appreciate his willingness to participate and his just a superb understanding of synthetic organic chemistry. With that, we'll introduce Drew and take it away.
All right, hello everybody. Thank you very much for coming. I'd like to take a moment and introduce and acknowledge my advisory committee. First, Dr. Christopher Jeffrey with the chemistry department. Like Glenn said, Dr. Jeffrey really, when we approached him with this project, he was really just gung-ho, jumped right into it, was very enthusiastic about it. And pretty much within a few minutes, he was able to find some literature which really kind of set the whole stage for this project, really. And Dr. Jeffrey was gracious enough to let me utilize his lab, utilize his knowledge of synthetic chemistry, and utilize his grad students. And all of them were very helpful in the completion of this project. So thank you very much, Dr. Jeffrey, for the help with this. Next is Dr. Elizabeth Ledger. She's right here in the front. Dr. Ledger really helped with the bring a critical perspective to the writing process of this whole ordeal. By the end of it, we had our data, we had everything, ready to go, but just kind of put it all on paper, and it didn't make a whole lot of sense. And Dr. Ledger was able to come in and take a look at it and tell us, no, this, and this, it all needs to change because it doesn't make scientific sense. And really throughout that, she was able to help us refine this process and refine the manuscript and make it from kind of okay to pretty good, in my opinion, pretty good. And finally, Dr. Glenn Miller. Glenn has been my mentor and my advisor pretty much since before I started grad school. I first took one of his classes as a junior, and he has really kind of shaped my philosophy on environmental science in general. The philosophy where it's best to be literate and skilled in chemistry when taking a approach to environmental science. And so Dr. Miller's probably forgotten a lot more about environmental science than I could ever hope to learn, and so I'm really, really lucky to have I'm very lucky to have Glenn as an advisor, so Glenn, thank you very much. These are many of the students in Chris's lab. I mentioned them earlier. I really could not have done it without these guys and their love and support. I wasn't quite sure what to expect going into this strange chemistry lab. Strange people practicing a skill that I had very little skill in, and they were incredibly welcoming and warm, and they treated me like an equal and like one of them. It didn't matter that I was part of a different department, and so a few of the members of the lab are here in the audience today, and guys, I'm so glad that you came, and I'm so glad that I got to work with you, and thank you very much. A few other people that are very important to me are in the audience today. First is my girlfriend, Haley. Haley, she has been incredibly supportive throughout this whole thesis writing and this whole, master's degree in general. She believes in me way more than I believe in myself, and she's been there to help me through when it's been really hard. So, thanks, Haley. My brother Gabriel's here somewhere. There he is. Gabe graduated recently with his degree in biochemistry, and he and I compete quite a bit. And so I'm glad that he's here today to see that I'm winning. Both my parents are here today, Renee and Richard. They've shaped my world, they've shaped me as a person, made me who I am today. They gave me a little bit of creativity and a little bit of practicality, and I think that I turned out okay. So, but my dad came from San Francisco to be here today. My mom came from work. She had to get time off of work. So to both of you, thank you for being here. And thank you for making me. Okay. All right. Lastly, I'd like to thank all of you for being here. If you're here, it means that you're supporting me, that you're here to see me succeed. And so I'm very, very grateful that you're here. Please help yourself to donuts and fruit. And at any point, I won't be distracted if you get up and get some in the middle of the presentation, because it is going to be a little long. Okay, let's get started. Here's my outline. I'm going to talk about the background, a little bit of beavers as very influential engineers of their environment. We'll talk about beavers as pests. We'll talk a little bit about aspen and how this project came about. Research questions. We'll go into the methodology, how I answered those questions, talk about my results, and talk about the conclusions, what exactly those results mean. Okay, so beavers as environmental engineers. So beaver are a keystone species. Now what that means is that keystone species, they have a disproportionately large effect on their environment relative to their abundance in the environment. It's really not hard to tell how a beaver is so influential on its environment. You can see one right here, cutting down a whole tree. They build their dams, they build their lodges, they build riparian ecosystems and expand them extensively. Through their activity, they, like I said, build riparian ecosystems. The sediment buildup behind their dams can repair damaged streams and incised streams. And especially around here, they create habitat for fish that, especially around here with the Lahat and cutthroat, are endangered. And the pools that form behind beaver dams can provide relatively safe and good homes for these fish. So in general, beavers, they provide a service that is really unlike anything else that any other organism provides for the environment. And we have a very strong vested interest in protecting them and keeping them around in our ecosystems. But when beaver and humans mix, it tends to not go well. This picture is from Elk Grove with this blocked drainage line that you can see has been blocked by a beaver dam there. Beavers in general, they are awful when it comes to interacting with humans. They destroy stuff, they just cut down the trees that we want to have, they'll destroy infrastructure, they can hurt dams and levees and dikes and those sorts of things. And generally speaking, they're huge pests when they encounter humans. And more often than not, how humans deal with beavers is, take them out, shoot them, trap them, poison them, whatever it is, it tends to not end well for the beaver. So we have this economic loss, and we also have the loss of beavers. We have a vested interest in both preserving the health of beavers, but also keeping them away from our space. So I'm going to switch gears a little bit and talk about aspen trees. Now, Glenn talked a little bit about John Basie and his discovery that there was a compound that existed in aspen trees which repelled beavers. He found that this compound that had previously been unidentified in aspen repelled beavers up to 80% of the time. Now, aspen, they're a favored food source of beavers. It depends on which study you read, but they're either the favorite or the second favorite food of beavers. It really doesn't matter. The point is they love to go after aspens, but the observation that Basie made was that these new sprouts, and I'll talk about the sprouts in a second, but these new sprouts that came up from a damaged aspen, the beavers generally wouldn't touch them, and there was really no good reason for this. The sprouts, they were numerous, they're small, they're easy to cut through, they're nutritionally dense, and it was that observation which led Basie to discover the presence of this previously unknown chemical and associate it with beaver repellent properties. So, aspen trees, they reproduce asexually by sending their roots out into the surrounding area, and then from those roots bud sprouts. And it was in these sprouts that the compound is in its highest concentration, and especially in the sprouts that are connected to a tree that has been cut down, such as by a beaver. So the beaver, because those sprouts have the highest concentration of this repellent chemical, the beaver are actually inducing a defensive compound being formed in these sprouts by nature of their activity in the area. Inducible defense is interesting because normally it wouldn't really make sense for an aspen or any other organism to create these compounds if there was no danger, if there was no threat. They have to invest energy, they have to invest resources in the creation of these metabolites, which would otherwise be better spent growing. So the fact that we see this chemical in the highest concentrations of the beaver-affected groves indicates that it is inducible defense. And we do see it in other groves, but not in nearly as great a concentration. So here are my research questions. Number one, based on historical structural data, can a likely carbon skeleton of the beaver repellent compound be synthesized? So basically we're going to identify what we think Basie had. Again, he never was able to figure out exactly the structure, and his research partner, Murray Hackett, who did most of the chemical identification of this compound, they were never able to fully nail down the structure. And so they have a big pile of data that just sat in a file cabinet for about 25 years. And based on those historical data, we attempted to create our best guess, essentially, at what it is that they were looking at. That was the target for our synthesis. Secondly, will the structural data of the synthetic product match the structural data of the chemical discovered by Basie? So this is our way of going back and proving that we have what Basie had. Essentially, if our structural data match the structural data taken 25 years ago, then we have a strong indication that either the compounds are identical or at least very, very close. And finally, can we find a chemical identical to the synthetic product in aspen extract? So does this chemical actually exist in nature, or did I just synthesize a big beaker full of garbage? That's the question that we are trying to answer with that. So this is the chemical, 1,3-dicinnamolyl-2-acetylglycerol. Now it's kind of beyond the purview of this talk to really give a good talk about chemical structure, but basically these lines all represent bonds. At the terminus of a line or at the place where it joins with another line, that's where atoms exist. Some of the atoms are marked, such as by these O's. They all represent oxygen. If an atom isn't marked, like with most of these, you assume that it's carbon. You also assume that the carbon's bonding orbitals are filled, and so if it's not full based on what's marked on the diagram, then you assume that the remainder of bonding orbitals are saturated by hydrogen. So the name also gives you a clue to the structure. Glycerol, starting with glycerol, is this central piece right here, is a derivative of glycerin, which is a fairly common household chemical. You find it in soap, you find it in a lot of consumer products. Cinnamolyl and dicinnamolyl is this part and this part, kind of the wings, so to speak, of this molecule. And as you might have guessed, cinnamolyl, that's a derivative of the compound that gives cinnamon its smell and its flavor. And finally, the final piece here is the acetyl group. That is a derivative of acetic acid, which is vinegar. So these aren't incredibly complex groups that we have brought together to make this molecule. We have glycerin, vinegar, and cinnamon, essentially, which is the pieces of which have created this larger molecule. So how did we come up with that as a target? we had a lot of clues. First of all, the very first one, and the one that Chris found, was a compound that had been discovered in 1977 by Asakawa et al. And they had found a chemical that matched this structure in a very close relative of aspen, which is Populus tremuloides. It's poplars. But we also have this spectra right here is from our most powerful analytical tool, which is called NMR. It stands for Nuclear Magnetic Resonance Spectroscopy. And basically what NMR is a very large magnet, and the individual atoms in a molecule act as smaller magnets. And so when you stick the small magnets inside the large magnet, they produce predictable and measurable disruptions in the large magnetic field. And this bumpy, jagged line here is what the instrument spits out. And a skilled chemist will be able to read that and interpret it and glean some structural clues from the readout of the NMR. So starting over here, and this is a segment of Murray Hackett's NMR from 1989, which he was attempting to identify the compound with. So this right here, we have a pair of doublet of doublets, which is just fun terminology, which refer to these two hydrogens and these two hydrogens. These hydrogens are associated with a carbon, making it a CH2 group. Now normally with CH2 groups, the hydrogens on there are chemically identical, which basically means you can take one and stick it in the other spot, and it doesn't affect the chemical environment of the molecule. But this one is a special one because both of these are neighboring to the stereogenic center. Now what a stereogenic center is in a molecule is essentially if the molecule, what it is the molecule has the potential to differ in its three-dimensional orientation about a stereogenic center. So the best way I can describe it is you have your hands, they're mirror images, but you can't really superimpose them. They're not identical, but they are mirror images. So in a similar way, we can have the possibility for two different molecules which are essentially mirror images of one another, but are not fundamentally identical. And what that causes is it causes these two hydrogens or protons, which would normally be chemically identical to one another, to actually be chemically distinct from one another. And so we have each of these interfering with the other one. It's like one magnet interfering with another one within the NMR. And they're also being interfered with by this central proton here, which produces this fairly distinctive doublet of doublet split pattern. And then over here, this kind of jumbly, jagged mess, a quintet of doublets, is this center atom, the center proton, which is being interfered with by the two or four protons surrounding it. And so this whole piece is very characteristic of a glycerin or a glycerol. We determined that there probably was one of those in the structure based on seeing this chemical fingerprint. Now, the second clue was this one. This is the cinnamoidal fingerprint, and we have in this region distinct patterns which correspond to this ring figure here. It's called an aromatic ring. And then we have this doublet and this doublet over here corresponding to this guy and this guy, who are both interfering with one another. Now, another interesting thing that we can do in NMR is we can determine the relative ratios of each atom to all of the other atoms in the molecule. And this entire motif showed up in a 2-to-1 ratio to everything else, which kind of gave us the inclination that there were two cinnamoids present, or cinnamides present. Because there are two of the entire motif, but there aren't separate peaks for each one, that gives us the indication that the two cinnamides are actually chemically identical, which would only occur if they were symmetrical within the molecule. There's only one way that we can attach two cinnamides to a glycerin and have it be symmetrical, so that gave us this structure right here. And then the final piece, the acetyl group went in the only other logical place that it could on the glycerin, and we came up with our target molecule. So, how do we synthesize it? Here's the first step. We use cinnamic acid as the first cinnamate and glycidol as the glyceric portion of our molecule. Now this was another one of Chris Jeffrey's wizardry techniques where if we had used glycerin by itself, it would have been fairly difficult to control where exactly the reaction occurred in space. And that is to say, it would have been difficult to make the cinnamic acid bond in this location and not down here, not over here. The glycidol is a derivative of glycerin, which is much more favorable for the reaction conditions that we were pursuing. And therefore, we were able to produce this key intermediate fairly easily. In the presence of a phase transfer catalyst, there was not need for heavy basic or acidic conditions. All it really needed was heat and time, and it produced this intermediate on its own. Fairly high yield, 80%. That's good in organic synthesis. Second step, not as good. So this one, we needed to attach the second cinnamate using an acid chloride attack with cinnamolyl chloride, which again is another derivative of cinnamon. This was base catalyzed, and we were able to get the bonds, the electrons from this bond to migrate over and attack right here, having the chlorine group leave, and all of that was catalyzed by basic conditions. Now this should give you an indication. The reaction occurred in 15 minutes at -20°C, and we still got only 22% yield. That was a fairly poor choice of reaction conditions on my part, largely because this stuff is such a hot reagent, it attacks everywhere. It attacks here, it attacks in both locations, and what it did was it produced a lot of garbage molecules that we needed to purify out in order to get this intermediate so that we could proceed to the next step. Regardless, we got enough that we were able to proceed with the synthesis and produce our final product, which was achieved by using base catalyzed acetic anhydride conditions to attach the acetyl group to the final bonding location. Right here, these R's, they're placeholders. I didn't have enough space to put the cinnamates in the slide, so these R's represent those. Anyway, we bonded the acetyl group to the final reaction location, and that was the completion of the synthesis. 3 steps. Overall yield was 15%. That's not great, again, mostly due to the second step being so inefficient. It lends itself to optimization, and we could very quickly increase the yield dramatically were that second step to be optimized. Future study. But
Next year?
What's that?
Is that next year?
That's it. Better be giving me a PhD. So how do we know that we have what we think we have? So I took my own NMR spectras of my product, and this is the proton NMR, the full spectrum. Right off the bat, we noticed some very similar things with the spectrum to the one that we saw previously. And the other one was blown up quite a bit. This is the full spectrum. But starting left to right, we have this doublet here and this one here, corresponding with the proton that's here and here. And again, they're not shown, but you assume they're there. The reason that there are only 2 peaks corresponding to each of those is because the one that's here and here, again, chemically identical to the other one. So we only see one set of peaks, even though there are 2 protons to which they refer. Again, we have this nice munge right here that refers to the aryl region, the aromatic rings. We have this little guy right here, that's the solvent peak. You have to dissolve the molecule in a solvent to make it work with the NMR. And a little bit of the solvent usually shows up in the spectrum, but we essentially ignore it. This guy right here is our quintet of doublets, which refers to the central atom right here. And just like in the other one, these are our doublets of doublets, which refer to the, again, chemically distinct protons that are associated with those. And finally, this big guy here is this methyl group right here on the acetyl group, which doesn't have any neighbors and it doesn't have any sort of stereochemistry associated with it. So that shows up as one nice clean peak. is the carbon NMR. It's similar, but on a much larger scale to the proton NMR. And again, I cut off half the molecule for the sake of fitting on the slide. One thing I'd like to point out is this region of peaks right here. It refers to the aromatic peaks. We have 1 and 3, 1 and 3, and 4 and 6. Those two are, again, chemically identical. So if we had the ring 1, 3, we could flip it around, produce no change in the chemistry of the molecule. And then everything else is here. Again, there's a solvent peak here as well. But we have a peak corresponding to every other carbon and nothing that doesn't correspond to anything. So we have our protons and our carbons. We know that they're there, but we're not 100% sure of where they are in space in 3 dimensions. And so that's where we get this COSY experiment that stands for correlation spectroscopy, and it's another NMR experiment that we can do. Up here is the proton spectrum. The same proton spectrum is on the y-axis here, and where they meet, where these dots are, if they are lined up with each other, that means that whatever peak this represents is correlated with whatever peak is over here. So this again is the natural peak that we see, and since it doesn't have any neighbors, it corresponds with itself only and no one else on either axis. This guy, however, our doublet of doublets, which refers to these two right here, they do have neighbors, right? That's all right. This guy refers to these here, my mistake. But anyway, this guy correlates with itself, but it also correlates with this little peak right here, which is our quintet of doublets. And as we see, these protons right here neighbor this central proton here. We know they're correlated. We know they're neighbors. Similarly with the aromatic region, and similarly with these two guys right here, which are actually represented by these peaks. Similar to that, HMBC, that stands for heteroatom mononuclear, no, heteronuclear monobond, multiple bond, bond correlation, which is essentially correlation of two different flavors of atoms. So in this case, hydrogen and carbon. I know that's very hard to read, but it's the same deal. One axis is up here. That's the proton. This one is the carbon spectrum, and where they meet in the center indicates correlation. And so we have this little nifty diagram here, which summarizes those data, since I know they're difficult to see. So here's a chart which basically summarizes all of our NMR information. In the first column, we've assigned each carbon a position on the molecule. We have the location of that carbon in the space of its NMR spectrum, the flavor of carbon, whether it's a CH, CH2, CH3, or C by itself. If it has an H, the corresponding proton spectrum information is right here, and then the HMBC data, which shows which atoms that one is correlated with. So all of this data taken together basically confirms that we have this and that there is no other possible atom that we could have. This next chart, this column represents the data from Murray Hackett's experiments. Okay, these are his proton NMR locations on the spectrum. And this is their information. Their the split of each peak, and the J coupling, which is a measure of how nearby atoms interact with one another. The proposed analog column is what I propose on my own spectrum is analogous to, or which piece is analogous to the piece on Hackett's spectrum. And again, here's this for reference. You see every single one of his peaks has an analog in my synthetic molecule, except for one, this little guy at 1.3 here. Now that can mean a few things. That can mean I overlooked something, but I actually got the structure wrong. Or, and this is the more likely explanation, because, and again, we can determine the relative ratios of the atoms to one another. This peak shows up in a ratio of 1 to 2 with the atom the central proton that we know there's only one of. So that would essentially mean that if this were a real peak, there would be half of a proton for every one of the others, which really doesn't make a lot of sense. This is about the area that water would show up, and so I proposed that it was water contamination. There's no way that I can go back and inspect his samples or inspect the instrument that he ran it on, so I can't say for sure, unfortunately, but I suspect that that's water contamination.
Plus the chemical shift in nitromethane?
Yeah.
Okay.
Yeah, he used a different solvent as well than I did, and his instrument was not as strong as the one that the chemistry department has. So that produces a little bit more error, a little bit more ambiguity in comparing the two spectra. So there's me on top of Mount Rose. Answering our final research question, does this stuff exist in the real world? So I collected aspen material from locations along Mount Rose, brought it back to the lab and freeze-dried it, ground it all up and extracted it with methanol. The extract basically gave me this gluey green substance that was essentially a cocktail of all of the molecules that I was able to extract out of the aspen material. And that material I sent through an instrument called an LCMS, which is a liquid chromatography mass spectrometer. The LCMS is very good at separating out very complex mixtures of molecules, and how it works is the chromatography portion of this instrument is essentially a column that you send material through, and it comes out, it elutes from the bottom of the column at different times based on its polarity and the size of the molecule. And what you can essentially do is send through a standard, which is a molecule that structure you know, and then send through your unknown molecule or your mix of molecules, compare the standard to the unknown, and get a good idea of what you have. In this case, my standard was the synthetic product. So I know this is very difficult to read, so I'll just sweep through that and get to here. The retention time, which is the amount of time that it took for our target molecule to elute from the column, with the aspen extract was 6.584 minutes. The synthetic product came out right at 6.58 minutes. And I have essentially identical mass. And the abundance of the synthetic was dramatically higher than the aspen extract.
So when you did the aspen extract, I'm just going to ask if you don't mind, just because I'm curious.
Sure.
Was that just targeting 394?
Yeah, we
Okay.
targeted that specific mass
Yeah.
based on the structure of my synthetic product. Which is another nifty little tool of LCMS, is you can target molecules by their mass and out to 5 decimal places. It's very precise. Again, so the concentration of the synthetic product, even though the concentration of the solution sent through the machine were identical, because the synthetic product was basically 100% product, and the aspen extract was a complex mixture of chemicals, it makes sense that it's significantly less abundant in the aspen extract. So what I did was I performed a spike-in experiment, wherein I essentially took 2 milliliters of the aspen extract solution and added 40 microliters of the synthetic product, not very much at all. With the idea being that if the molecules were different, we wouldn't see an appreciable difference in the abundance of the aspen extract. And as you can see, that's not the case. We have a significant difference between the extract by itself and the spike sample, which indicates that what we have, what we've synthesized in the lab, is essentially identical to this compound that we found in aspen trees. So, how'd it go? Oh yeah, there's me. The synthetic product is identical to the target crop. Okay. That answers our first research question, and we proved that with the NMR analysis along with the mass spectrum analysis of our synthetic product. We made what we set out to do. So dovetailing into that, the synthetic product is probably identical or very similar to Thesis compound. Now again, we have a little bit of uncertainty. There was that rogue peak that was probably water in the NMR that we're not sure of. And also, it's just not really possible for us to travel back in time and examine everything that we would need to examine of Thesis in order to definitively prove 100% beyond a shadow of a doubt that we have the same stuff. There are ways to get around that though, and I'll talk about them in a second. But first, we found my synthetic molecule in the wool, and that was demonstrated by the LCMS experiments. And thank you very much, Carissa, for taking this photograph. Very stellar image. So, where do we go from here? So the product can be commercialized, right? We talked about how detrimental beaver are to their environment, and with this compound, the application of it in conjunction with other physical barriers will be able to produce a repellent effect and keep beavers out of where we don't want them to be. However, in order to use this, in order to commercialize it, we need to study the compound's properties further. All I really studied was, can it be made and does it exist in the world? We don't know if it's toxic, we don't know if it will light these trees on fire simultaneously, or what it is that it will do. However, the synthesis and creating the synthesis pathway of this molecule will be helpful in that respect, essentially because we don't have to go and scrape a bunch of bark off of a bunch of trees like Basie did. We can make a decent amount of this product in less than 2 days in a lab. Again, the synthesis needs to be optimized. That second step, not very good at all. I think it really lends itself, though. It's easy to figure out why that step wasn't as efficient as it could have been, and I think that a skilled chemist would be able to optimize that step and optimize the entire synthesis in fairly short order. And finally, it makes sense for an aspen tree to create a defense against herbivory that works not only on beavers, but on a whole host of herbivores. So there is some anecdotal evidence that this works also on snow hares, and that hasn't been studied at all, so that's 100% anecdotal. But the idea that this compound might be more of a broad spectrum defense against herbivory rather than a beaver-specific compound is intriguing, and it's worth investigating. We don't know the mechanism of action, we don't know if it tastes bad, we don't know if it smells bad, so that a more skilled biologist than myself would be able to take that and run with it. And that's all. So thank you very much for coming. I hope you learned something. And
So I'm not going to worry, but I think something sneaky happened, and we might have made the wrong compound. So don't be too concerned. It's found in aspen, it's an analog. So if you go back to the first slide, and it's totally a weird set of coincidence that led to this. Oh yeah, so the slide with where you explain the coupling patterns, but in the aromatic region. Next one. Yeah. So this is a nicely resolved one, and I didn't catch this before. But there's a few characteristic things that kind of stand out. Now you see the similar doublet pattern in the stuff that you made in the proton, but is there something that's distinct that you see?
or this one.
Those two, yeah. So those two related peaks, they kind of have that little bit of cabbage down the bottom. Those are an AB quartet is what we call them, and it's distinctive for a certain structural feature. When I originally was looking at the NMR spectra, I was looking at the less resolved one, in nitromethane, and this is why it's important to take your synthetic stuff and put in nitromethane just to confirm maybe what we're seeing. So what I think has happened is that if you look at your synthetic proton NMR, so you can fast forward to that one. Yeah. So it looks like if we go on to the 7.5, it's not as zoomed in, right? It looks like we still have that same double pattern, but what's different?
They're much closer together in the field.
They're closer together, that's fine. That might be solvent, right? So that was tricky. So I was willing to accept that error. What's different? What about the area under the peak? The right side
Right.
peak versus the left.
Yeah, this course, or this integrates to
Uh-huh.
3.
Yeah.
This one is 2.
So what I think it is actually, is that I think we have a parahydroxycinnamate, and that's the real structure. Uh-huh.
And that's where the OH came from?
Yep,
And
and that's where the
so is the
1.3 peak comes from as well. It's about all of the data. This is common, this is why we make molecules, to correct them. But I think that's the true structure, is parahydroxy.
So essentially this with, at some point here.
On the para, because you have to have the symmetry. And I'm pretty convinced of it, and also that will separate the two doublets even more in terms of chemical shift. So you made a compound that's an aspen, and it you know, it's a weird coincidence that we have coincidental overlap of one of the peaks. No spectrum could tell us that.
So why does the mass spectrometer?
Yeah, so that's because they were looking for the peak at 394. That's why I asked if they were searching for that specific peak, which means it's an aspen, but I bet you if you search the analog with 2 more hydroxys plus 32 AMU, you'll find that, and it might even be more abundant.
We also found in the spectrum a lot of analogs that were
In the mass.
significantly high. Yeah, in the mass.
They were
was
higher.
Significantly higher, and Casey was explaining that to me as they had picked up sodium in the instrument.
Oh yeah, it's going to pick up sodium. That's the only way it can ionize and be in the gas phase, or one of those. And these types of glycerol derivatives will pick up sodium pretty readily. The thing is, yeah, so I bet you what would be good is to re-inject the natural stuff and see even if it's in more abundance, the parahydroxy. It's an easy synthesis. You've already established synthesis, so we just use parahydroxycinnamyl chloride and make that compound. But I bet you you'll see that the other thing is that it was hard to see the consistency with the NMR spectrum, again, because of the solvent. But the parahydroxycinnamate will definitely have a different carbon chemical shift for the hydroxylated carbon on the aromatic ring. Yeah. I caught it just now. After looking at your data multiple times. This is why we make molecules. So, yeah, but it's
interesting. I realized very early on that arguing with Chris was losing out. But there was 3 compounds that were found in the trebinoides. And they were, one was the cinnamate, the other one was a parahydroxylated on both sides, and one was a split, I think is the 3 of them. So they're all 3 of them were made in the system. So but this was laid out really nicely, though.
Oh, yeah. Oh, no. It led to the structure. It still led to the structure determination. And, you know, you said it takes 3 days to make. So let's make it.
Is there any less critical comments?
I'm criticizing myself. I came to the wrong conclusion.
You mentioned that someone previously had spread something on aspens to test against the repellent, or test on other plants to test the beaver repellent.
Yeah.
Was that just the extract, or was that like isolated compound?
Yeah, no, it was the extract that had been partially isolated.
Oh.
And all they really did was dissolve it in methanol, paint it on the trees, and do a rotating control group, methanol only, and extract group.
It's called a cafeteria experiment.
Yeah, cafeteria style.
And it
feeding
was really
Yeah.
conclusive, and he had isolated the component by electron chromatography in a big column. I think he got.
Yeah, I should have mentioned that Dr. Miller was the advisor for the papers that came
Steve
out.
Jenkins, I was just a chemistry guy. John did a lot of work on all that. Guy from all kinds of crazy.
I think you said this in the beginning, but is this compound specific only for aspen, or are you wondering
No.
if it's in other plants?
So the first guy to find it and actually demonstrate the structure was Asakawa, that came about 20 years before this, before Basie got a hold of this. What he did was he essentially found it as part of a suite of similarly related compounds in the bark of poplars, which are close relatives of aspens. He did not confirm that there was a link, or he didn't even study that there was a link with beaver herbivory. He just found the molecule.
The reason I asked that is because it kind of goes back to your last slide. You were saying that you want to see if this has biological activity potential towards other herbivores. And it made me think of birch trees, because in the east, birch trees grow vegetative like aspen, and deer will not eat them. And it kind of made me wonder if that compound's also present in those saplings.
So,
So it could be, like you said, like a big deterrent against herbivores.
secondary metabolites in plants that are specific defenses against herbivory, ridiculously common. Most spices are the result of that. The Jeffrey lab is working on that in the caveat. Be correct. I wouldn't be at all surprised if there was some similar thing or even the exact same stuff working to repel the deer.
Perihydroxycinnamic acid is the thing that they just found in the royal jelly of bees that determines their sex, where the queen can dope that into the...
It's funny that you say that, because they found that in propolis from bees, which is bee glue, essentially.
I mean, there are all kinds of analogs that way. It makes synthetic sense.
Any other comments? I've thoroughly enjoyed, this is one of my career goals, is to get this resolved, and Drew and Chris have rounded out this project, because we started, well, it was in the mid-'80s, and then Murray Hackett actually looked at it in the mid-'90s. He got some more spectra, although I think he used spectra than we'd gotten from Davis, so it was
So 3 more days?
well,
Come on, Drew.
As the ecologist, I have to say that even if this is not the compound that they isolated in 1985, this could still totally repel creatures.
Right, yeah.
Definitely.
They're
Oh, it
not
should be
gonna-
tested, and it is
Exactly.
found in aspen.
And
I'm
maybe
convinced
this
of that.
does it too.
They're
So,
not going to come
right,
along
like,
and be like,
Oh, yeah.
"Whoa, there's a perihydroxy on that."
Oh, no, I'm...
No, thank you.
You never know, but
It's possible.
It's possible it's more potent and more abundant. It's just that, and you found it in aspen. I mean, this compound is in aspen, the sprouts.
No
The
question.
mass spec, there's no question about that. I'm not saying that. What I'm saying is the NMR spectrum, and it's, I mean, I've never seen such a coincidence where you just have that coincidental overlap that matches the same pattern. And you
just
can't
the
even see it.
integration.
Oh
was what-
yeah, it was just a subtle difference in integration, and then seeing this blown up on the slide, you know, in a large area that now lends me to think that I know what the structure is.
So how concentrated is the natural compound in?
In the aspen I found, not very. So I collected the aspen from areas that did not have beaver activity, and the concentration. So let's find the slide. This abundance was present in the synthetic solution that I sent through, which the chemical in its pure form diluted down to 1 microgram per milliliter, which incredibly small, incredibly large solution, produces a number in the abundance column that is orders of magnitude larger than the extract diluted to the same dilution.
What'll be interesting is look for the one that's plus 32 now, in that same mass spec, and see if you have like a crazy abundance of that. The one that has the 2 oxygens.
I think that's useful. I'm going to get my biologist friend here to help identify, because the amount that was found in he called it juvenile form, which isn't very specific either, but you cut down, go to aspen forests, cut down, all these sprouts come up, or these trees come up, you cut those, and then you shave the bark off those and compared that with the bark of the mature aspen, very, very small amounts, and this was the largest peak in UV absorbance. That doesn't tell you a whole lot, but comparatively, it was probably 2 orders of magnitude higher in the sprouts that came out. So it was a very distinctive HPLC peak that we did not find in the mature form. So it was kind of knock your socks off. That's why we could isolate it, because there's a lot of it in those.
Yeah, so it'd be interesting to go back to that data and do that. I do have a more ecological question if we have time. If you guys don't mind.
Sure.
So you mentioned induced offense a number of times.
Mhm.
So you, it's fine. I'm not going to criticize induced offenses. So you mentioned that it's you have this parent form, the sprouts come out, same root system. It's got more of this compound in those, and you affiliate that to being an induced offense. I think you need to do more tests to confirm that it's an induced offense. And what would you think that you would do?
So in that case, the best way to do it would be, in my opinion, find a location that no beavers are there, and find two analogous trees, determine where their offspring come up, and then cut one of them down. Come back a few weeks later, and
Yeah, and so you would have to test the hypothesis, because it could just be that it's the developmental, during the development of the sprout and then to the adult tree, the metabolism is plastic, like it changes a lot.
And
We see that with a lot of different plants, so it's you have to do some careful experimentation to see if it's actually induced or if it's just inherent to the developmental change of this ontogeny that is happening over the development.
You know, Basie would say that you could see, you go to a place that's unaffected by beaver, nothing's cut down.
Mhm.
You can take down those little sprouts that come up naturally, as Drew's,
Yeah.
nothing there.
Huh.
It has to be cut down. There has to be damage done to
it
it.
would make sense though. The younger sprouts, they haven't invested as much resources in like their bark, their
It changes.
thickness.
Yeah, their
Yeah.
metabolism does change over development. So, and that could have been the baseline of kind of making that defense, is that they were metabolically distinct, and then they gained advantage by making more.
Anything else? I want to thank Drew, that was an excellent presentation. As Drew said, grab some,
Yeah. I don't want to.
Yeah, deterres deer though. They can sell it and people love it for their gardens. Yeah, they're so detrimental.
Well, Carson would like it.
No, that's what I'm saying. Because apparently the deer are destroying biodiversity. I wouldn't have anything on that.
No.